All right, take two. We're trying this again. This is week 4 problem session. We're going to start off with questions asked about the homework, because that was by far the majority of the problems asked for this week. So we're going to start off with doing a problem like number 1. And this one gives away the game a little bit more than a lot of these do, even doing one like the problems. Because this one is, I'll admit, a little bit of a trick question, right? Because this is in the same homework where we learned about trig limits. At least I think it is. It's the same homework where we learned about trig limits. And this looks an awful lot like one of our trig limits that says the limit as theta goes to 0 of sine theta over theta is equal to 1. Right? But there's two key things about this statement that are very important. One of them is that whatever we plug into sine has to be the same as what's on the bottom. Right? So if it was sine of 3 theta over 3 theta, we'd be fine. If it was sine of theta over 2 divided by theta over 2, we'd be fine. As long as whatever's plugged into the sine is the same thing as whatever's on the denominator. The other thing that needs to be true is that whatever this thing is that matches needs to be going to 0. Right? So whatever is inside the sign and therefore also on the denominator of the fraction needs to be something that's going to 0 in the limit. Right? So if we look at this problem over here, what's in the sign matches with what's on the denominator, but that thing is not going to 0. So this problem is not a trig limit, right? Or at least it doesn't use our two special trig limits that we learned about in these sections, right? So we're left with the first step we really should do for any limit whatsoever, which is substitution. Right? So we substitute, we get sine of 4 pi over 3 over 4 pi over 3. Right? I'm going to simplify that denominator because dividing by a fraction is the same thing as multiplying by the reciprocal. Right? Now, to figure out sine of 4 pi over 3, right? First off, I know that 4 pi over 3 is not in quadrant 1. In fact, 4 pi over 3 is somewhere over here in quadrant 3, right? And over in that quadrant, the y-coordinate and the x-coordinate, for that matter, are negative. So that means that sine of 4 pi over 3 is equal to negative sine of its reference angle, right? And if it's one of the sort of standard memorization tables of angles, it's not too bad to find the reference angle. You just take the numerator and put it under a regular pi. Right, so this is going to be negative 3 over 4 pi times sine of pi over 3. That's one that we should have memorized. And it is root 3 over 2. And so our final answer is going to be root 3 times negative 3 all over 8 pi. Right. So this one's not actually a trig limit, because the variable that's inside, or the expression that's inside sine, is not going to 0. So we treat it like any other limit, which means our first step is always going to be substitution. There's nothing undefined here. Nothing went to infinity. Nothing's being divided by 0. So our substitution was legal, and that makes that guy our final answer. So I'm just going to check real quick. Okay, we're still going. I'm not going to do that after every problem, but I'm going to do it after the next few because I don't want to get too far and then lose stuff. So the next question that was requested was to do one like number 3. So that's going to look like the limit as t goes to 0 of root 3 over 2 plus 3 tangent of t all over t. Right, so if we do substitution, because it doesn't look like anything we know about right off the bat, right, we get root 3 of 3 times tangent of 0 all over 0, 0. And if we recall our basic trig values, that is tangent of 0 is 0, so we have an indeterminate form. Right? So, indeterminate form, if we're going to deal with that algebraically, that means we have to factor and cancel, right? Now, we could do that for our root here, right? But the trick with factoring is you're supposed to factor out the thing that is becoming 0, right? The whole problem with this indeterminate form is you have 0 over 0. So if you factor something out and cancel it, but that something didn't have anything to do with it turning 0, canceling it out is not going to help, and probably not going to be possible for that matter. But the important thing is that it's not going to help, right? And this root piece is not the thing going to 0, right? Root 3 over 3 is a perfectly fine number. The problem is this guy. The problem is tangent of 0, right? So that's the thing that's going to 0, and there's nothing we can factor there, right? But thankfully, algebraically is not our only trick for dealing with indeterminate forms anymore. We now have trig limits, right? That was the other thing introduced in this section. So we need to somehow bring into play sine theta over theta, or 1 minus cosine theta over theta. Where theta, it doesn't matter what that name is, it's just something that we plug into sine that's the same as the denominator, or something we plug into cosine that's same as the denominator. Right, so it looks like t is going to be our version of theta in this problem, because that's what's in the bottom and that's what's being plugged into the trig function. But trig limits need a sine or cosine. So if you have something where it looks like you're going to have to use trig limits, or that's the method you've decided to pursue, and it doesn't have sines or cosines in it, then you're going to want to turn it into sines or cosines. So we're going to have the limit as t goes to 0 of the cube root of 2t plus 3. And to turn tangent into sines and cosines, we're going to use the quotient identity. Right? And then I'm going to simplify this because you can always take a factor of the numerator off of the numerator and turn it into a factor of the entire fraction. Right? And then product of fractions says we can combine everything there, but we don't have complex fractions anymore, which is nice. And I can also see as part of this one of our trig limits. Right? We don't have a 1 minus cosine theta, so that cosine t hopefully just won't screw things up, but we do have a sine theta over theta. Right? So maybe we want to rewrite this. The limit of t goes to 0 of sine t over t times that cube root over cosine t. Now the product rule for limits says that we can split this up in factors as long as these two limits that we're coming up with here exist, right? So this is going to be questionable whether we're allowed, but for this type of problem, we always do it, work through it, and at the end, if for some reason one of these limits doesn't exist, that doesn't mean this question mark indicates that this limit that we're working on here not existing doesn't mean that the one that we care about doesn't exist, right? It means we have to come up with some other way to deal with it. But thankfully for us, we know that the limit of something over that same something as that same something goes to 0 is 1. And over here we can do substitution. Right? Cosine of 0 is just 1. So we get root 3 of 3. Right? So the trick with these is it's indeterminate form. We can't factor out the piece that makes it 0. But the piece that makes it 0 up top is a trig function. So maybe we can use our trig limits. Trig limits require sine and cosine, so we've got to get them out there. Then we do some algebraic manipulation stuff to find one of our trig limit forms. Then we use the product rule down here. And then we're done. We're solid with that one. So checking yet again. Okay. I'm pretty confident we're going to be good for the rest of the time. I'm not promising I'm not going to check though. Okay. So I was also asked about 6, and I was asked about 7, and the trick with both of those is that they're the exact same problems with different numbers. So if I'm just going to do a problem like it but change the numbers, I'm going to do one of them for both of them, because if I change the numbers between the two, it's the exact same type of problem. So let's do limit as x goes to infinity. I think this was the next one I need to do. Yeah. Okay, cool. Limit as x goes to infinity of the cube root of 2x to the 9 plus 3x to the 7 minus 2x to the 5th plus 3x minus 10 all over 10 minus 2x plus 11x cubed. Right? So the trick that we learned in 2.7 for these is, as crazy as these rational or rational-esque, these algebraic functions might get, we can boil them down if they're still basically polynomials on the top and bottom, or roots of polynomials on the top and bottom. We can boil this down to a limit that's still of a fraction, but it's of a fraction of their leading terms, not of the full thing, right? So looking down here at the denominator, right, the leading term is the term with the highest power. So the highest power here is cubed. So that's our leading term, right? And looking up here, up top, everything's under the same root, which is nice. So we can just pick the highest power under the root and leave it under the root, but throw away the rest of the stuff, right? So all of these problems where you have a function that looks like a quotient of either two polynomials or polynomials with roots over them, you just take the leading term and the limits of the full function that you care about, and this quotient of the leading terms is exactly the same. Right, so we can do some algebra here. We get the cube root of 2 for that. And so the cube root of x to the 9th. Remember, cube root is raising it to the 1/3 power. Right, so we can, since that's a product, we can split roots up on products. And then we can use our rules about exponents to know that that guy up top is just x cubed. Right. And then, hey, it turns out our x cubes cancel, and we get the limit as x goes to infinity of the cube root of 2 over 11. Since there's no x's there, it doesn't matter what x is doing, right? Any limit whatsoever of a constant is just that constant, right? Now, these ones, 6 and 7, should all, you'll want to confirm it, but, well, no, they'll all work out so that you can pull this leading term off, and even if you don't get them to cancel like this, right, the next problem we're going to do is going to talk about how to deal with it there. But this is what we have for problems like 6 and 7. So the next one asked about was like number 8. And I'm not actually going to do one like number 8. For one, because there are like 7 pieces. A, B, C, D, E, F, G, H, I, J. Sorry, 10 pieces. But also because this problem is purely asking you to look at a table of the rules and apply them, right? There's not any algebra you have to do. There's not any manipulation. There's not any process. There is a match this up with a list of rules and come up with the answer, right? So what I'm gonna do here for this is remind us what the rules are, right? So first off, the limit as x goes to infinity of x to any positive power whatsoever, right? So the important thing here is it's positive, is equal to infinity, right? If you're multiplying a number that gets bigger and bigger and bigger and bigger by itself, however many times, then it's going to keep getting bigger, right? On the other hand, if you have a negative number, right? So if the power is negative at all, right? Well, we need to remember that this is the limit as x goes to infinity of 1 over x to the n, right? Remember, that's what a negative power does, is it shoots it to the bottom. And 1 being divided by a number that goes to infinity is going to 0, right? So if x is going to infinity and it's being raised to a negative power, no matter what that negative power is, if the power is negative, then it's going to 0. Similarly, if we have the limit as x is going to negative infinity of x to the negative n, then that's going to 0 as well. Right, so we're in the same case here. The trickier one for power functions is the limit as x goes to infinity. Negative infinity. We already did infinity. Of x to the n. Again, n is positive here, right? That's why I've sort of split them up into these 2 columns, right? There's 2 possibilities in this case. One possibility is that it goes to positive infinity, and this is if n is even, right? So if n is even, then we're multiplying a number that gets more and more and more and more and more and more negative, right? It gets big on the negative side. But if you're multiplying it by itself an even number of times, all those negatives cancel, and you just get a really big number, period. On the other hand, if you're multiplying it by itself an odd number of times, then the negatives don't cancel, and you have that this whole thing is going to negative infinity, right? And we talked about this a little bit. If n is a fraction, right? So in other words, if we're talking about a root situation, then the numerator being odd or even is what tells us how to do it. Right? So, for example, if we had the limit as x goes to infinity of the cube root, sorry, this needs to be negative infinity still, of x to the 10, right? In other words, this is the limit as x goes to negative infinity of x to the 10^3, right? So it is a power function like we have here, even though it might not look like it. In itself, the power itself can't be even or odd, because fractions aren't even or odd. But this rule tells us to look at the numerator. That's even, so this is going to be infinity. All right. Okay. And this guy just, it doesn't matter whether this is a fraction or a whole number or what, as long as it's positive, it goes to the same place. All right. So other rules that apply here. So these rules will work for parts A, B, C, D, I, and J, if I recall correctly. So for parts E and F, the book tells us that the limit of e to the x is equal to infinity, but there's nothing special about e there. The limit as x goes to infinity of any number whatsoever to the x is going to infinity, right? Because the graph of our exponential functions looks like this, right? And it doesn't matter what the base is. The base tells us what this value is, right? It tells us sort of how high we get how quickly, but the picture always looks like this, right? So this picture also tells us that the limit as x goes to negative infinity of e to the x is going to be the same as the limit as x goes to negative infinity of b to the x. And if we recall how this graph works, it has a horizontal asymptote at 0, because no matter how small you just get closer and closer to 0. Right? So this works for parts E and F. And lastly, some things we learn in that section, or by looking at a graph again, the limit of every logarithm. The book might just tell us about the natural logarithm, but again, the base doesn't matter. As x goes to infinity is going to be infinity. And again, we can see that from the graph that looks like this. No matter what the base is, a logarithm graph looks like this. Right? And this is, in fact, the only logarithm rule, because since you're not allowed to plug negative numbers into a logarithm, the limit as x goes to negative infinity of a log doesn't exist. Right? So this should help with G and H. Right? So the last sort of thing that you might need to do a problem here in 8 is to remember the constant multiple rule, and that negative, so this is an example, -4 times infinity is going to get you to the same place as negative infinity, and -3 times negative infinity is going to get you to the same place as positive infinity. Right? So remember your constant multiple rule. Pay attention to what the problem's asking. And remember that if you multiply a non-zero number times infinity, you're going to get an infinity back, but it might change the sign. Right? So number 8 is really just practice using these rules. All right. Check again. Okay, good. That's going to be very sad. So we're also asked, like number 9. So choose all delta that would... I didn't write down the precise verbiage of this. But the basic gist of what it's asking is to show that the limit as x is going to 3 of 2x minus 4 is equal to 2 with epsilon equaling 0.4. Right? So when we look at that formal definition, it says for all epsilon, there is a delta. Right? So one of the things that should mean is that if someone hands us an epsilon, we should be able to tell them at least one delta that works. Right? Now this problem and I believe number 12, right? So this is actually like number 9 and number 12, because these are, again, the exact same problems with different numbers plugged in. So since all I would be doing is plugging different numbers in, I'm going to do one problem for both of them. They both work exactly the same way. So both of these on the program are multiple choice, right? That's why I have this choose all here, right? And we'll see how that works when we get to the end of this, right? So the definition, the formal definition that we have is that we want the absolute value of f of x minus L to be less than epsilon when x minus c is less than delta, right? So to plug in for this problem, this is our f of x, this is our L, and this is our c. So we want 2x minus 4 minus 2, right? 2x minus 4 is our f of x, 2 is our L, to be less than 0.4, according to this problem, when x minus 3 is less than delta. So whenever we get a problem involving the formal definition, we're going to start by manipulating this guy. This piece is going to come in at the very end, and this piece is going to come in somewhere in the middle. Right? So working with this guy, we get 2x minus 6. One of the things when I say working with that guy, the main thing that we're trying to do is make this piece show up somehow using algebra. Right? In this case, it's not too bad. We can pull a 2 out, and we get that guy right away. Now, one thing that we do all the time without thinking about it in algebra is we replace one thing by another if we know they're equal, right? If we know x equals 2, we can replace all of our x's with 2. Now, we can do the same thing with inequalities as long as we keep the same inequality there, right? So I can replace x minus 3 with delta as long as instead of saying it's equal, I say it's less than, right? And hey, we want to show that this guy is less than epsilon. We've already shown that this guy is less than 2 times delta. So as long as 2 times delta is less than 0.4, then we have what we want, right? So remember, this is what we want to be true. This is what we know is true, right? So we know it's true, and that's how we did this substitution. We want this to be true, and that's how we do this substitution, right? So now we need to solve for delta and figure out what delta has to be for that to be true. So we have 2 delta is less than 0.4. So delta, we can divide by constants, and as long as they're positive, nothing changes. So as long as delta is less than 0.2, then it will satisfy the formal definition for that epsilon. So on the computer, what you would do is you would go through and you would choose every single one of the deltas they offer you that is less than 0.2, right? And technically, we probably want to say less than or equal to. I don't know if that comes up for the computer, but since this guy is strictly less than, this guy can be less than or equal to. So best to go ahead and assume that, right? Again, the multiple choice means it's not as big a deal, but as long as we are less than or equal to 0.2, then this statement demands that this statement be true because of the algebra that we did here, right? So the process for these problems is we always start off with the f of x minus L piece, and we do algebra to that piece until we can get x minus c somewhere, right? And sometimes we're lucky enough that that's it. That's all we have to do. We replace the x minus c with delta. We figure out that that has to be less than or equal to epsilon, and we're done, right? Now, sometimes we have to do an extra step, and that's what happens in problems 10 and I believe 11. So like 10, we'll talk about 11 in a second. 11 is actually just like 9 and 12, except instead of, so if this were like 11, like number 11, then we would have delta is less than or equal to epsilon over 2, and this would be our final answer, right? So in 11, it doesn't tell you what epsilon is, but it wants you to give your answer as a formula that has epsilon in it, right? So our answer here would be, instead of plugging in a particular epsilon, we just leave epsilon as a variable. So we would do exactly the same work. It's just here we would have epsilon, and that looks like we're multiplying by it, so I won't do that, right? So I'll do this, right? So here we would have epsilon, here we would have epsilon, here we would have epsilon, so our final answer would be this. But it would be the exact same process. It's doing the exact same thing. It's looking at f of x minus L, working until we get x minus c, replacing that with delta, and then solving for delta, right? So 10 is the one where we get trickier. Right, so for number 10, this is another one where we don't have epsilon, so we'll kind of see the differences. One of the differences between 9 and 12 and 11, we'll see a little bit here in number 10. But again, this one's going to be a little trickier. So we're going to have the limit, or we're going to want to show that the limit as x goes to 1 of x squared plus 3x equals 4. And we want to find delta from the formal definition as a function of epsilon. And that just means that our final answer is going to have epsilon in it, right? So our f of x is x squared plus 3x. Our L is 4. Our C is 1. Right, so f of x, L, and C. So we want f of x minus L to be less than epsilon when we know x minus 1 is less than delta. Right, so same as before, we're going to start with this piece. We're going to start with f of x minus L, and we're going to try to find x minus c in there, right? And in this case, finding x minus c is going to mean factoring, right? And we can see that x minus 1, x plus 4 is a good factor of it. And one of the nice things about absolute value is you can break it up by factors. So here we have x minus c, the absolute value of x minus c. So we can replace this with delta and have a less than. Now here's where the tricky bit comes in, because if we did like we did before, we would say that delta is going to be less than or equal to epsilon divided by the absolute value of x plus 4. And we don't want a function of x. We want a function of epsilon, right? That's what the question is asking for, which means that the only variable allowed is epsilon. We're not allowed to have x as a variable. So, what we want to do is presume delta is less than 1, right? So if we think about this, if we think about the definition that we have here, the wording that we used for this way back the first time we looked at this, right, when we looked at the informal definition, this means that x is close to -1, right? So it means that x minus 1 is less than 1 if we want to look at it algebraically, right? If we recall from way back in pre-calculus how absolute value inequalities work, this means that -1 is less than x minus 1 is less than 1, right? So that tells me that 0 is less than x is less than 2. So the whole reason for doing this is that I want to replace this statement right here with something that I know for absolutely certain is bigger than it, right? Because in this whole time, we're always replacing with things that are bigger than it, right? So if x is always going to be less than 2, right, which we have from this statement, which we have from this presumption, if x is always going to be less than 2, then in that case, x plus 4 has to be less than 6, right? If x can't be bigger than 2, then x plus 4 can't be bigger than 6, right? So this was sort of a side thought. So if we continue with this line from up above, right, we know that delta times x plus 4 has to be less than delta times 6, right? And we want that to be less than or equal to epsilon, right? Because in the end, what we want is to say that this guy is less than epsilon, right? So delta is less than or equal to epsilon divided by 6. So technically, if you were doing this like in real life for me, You need to note that delta is either epsilon minus 6 or 1 if 1 is smaller than epsilon minus 6. For the problem, it wants it as a function of epsilon. So for the computer, for the homework, this is your final answer. This would be something you would include if it was on the exam or something. Right? If you were doing it out in writing, for me, you would need to note that delta also has to be less than 1. Regardless of what else you might find, since you said this, delta has to be less than 1. You're always allowed to say that because delta is whatever you decide it is. Right? Delta is something that you, the problem worker, get to figure out. Or get to say what it is. So if you want it to always be less than 1, it's always at least less than 1. Right? But the epsilon also gives us a restriction, and that's the one that the computer wants. Right? So again, this is similar to how 11 is going to work out, except you won't have to do this step. Right? This step is something that's just going to show up if you're doing a quadratic f of x. 9, 11, and 12 are all linear f of x's, so they are all going to have the algebra work look like this. Right? They just might have a slightly different way to get to a final answer, depending on whether epsilon is a specific number or you want to have a function of epsilon. Right? And with that, I think that is all of the homework problems that were asked about. Yeah, I think we have covered all of them. So we can start to talk about, oh, thank God, we can start to talk about other problems. So first, there was only one problem from section 2.9, and we're actually going to get through it really quick, because that type of question is not really something we're going to worry about in this class. So I'll go ahead and write that out for people who are just watching along and not listening. Though if you are really interested in problems like that, because those are interesting and exciting problems, I just don't want to stress out the whole class with going over problems that aren't really applicable for what you need to know for this class. But if you are interested in it, you might want to come talk to me about majoring in math. That's a type of question that we like to answer, and it's definitely a gateway drug into it. So, but for now, for purposes of the entire class, don't worry about it for what we need to know here. So I just wanted to get that quickly. So the next one was from section 3.1, number 17. So that looked like me failing to write it down entirely. So this was use the limit definition to calculate the derivative of f of x equals 7x minus 9. So, the definition of the derivative, we have f prime of a is equal to the limit. Well, there was two different definitions we had. I chose this one for a linear function. It really doesn't matter. Yeah, I chose this one because it's just more the one I'm used to dealing with. So our definition here was f of a plus h minus f of a all over h. So this is going to be the limit as h goes to 0 of 7 times a plus h minus 9 minus 7a minus 9 all over h. So we get the limit as h goes to 0 of 7a plus 7h minus 9 minus 7a plus 9, because we got to distribute that negative to both pieces, all over h. The 7a and the negative 7a cancel out. The negative 9 and the positive 9 cancel out. So we're left with the limit as h approaches 0 of 7h over h. The h's cancel out, and we get the limit as h goes to 0 of 7. 7 doesn't care about what h is doing. It just stays 7. So we get that the derivative of that linear function is, in fact, the slope as we should have expected it to be. Right? But it did specify in the directions, use the limit definition. So since we knew what it was going to be, we should just use that to check ourselves. Right? Okay, so the other one from this section is really tricky for me to do. I'm going to have to talk out a lot, because one of the things, the GU, if I understand what that symbol means, that means do it on a computer. And I can't really show you that because, one, the calculator makes my iPad crash, and two, no, it's really just that it makes my iPad crash. Right, so this problem is, first it says plot f of x equals x to the x. And I can give a sketch of that. So it does something like this, right? And it says, well, it actually doesn't say use that. It says use a plot. So use, I can spell. Use a plot of f of x equals x min x to estimate a value c such that f prime of c equals 0. To sufficient accuracy so that f of c plus h minus f of c all over h is less than 0.006 for h equals 0.012. So this is another one where you don't need to worry about it too much for this class. This is not really focused on too much numerical methods. Looking at a calculator and guessing and checking is not really a process that I'm going to be focused too much on. But it is one that is maybe a little bit more useful for folks than 2.925 would be, unless you're going to become a math major. But the way you would do this is that this, recall, means that the tangent line is flat, right? So the C that they want is right about here. So what you would do is you would graph this on something, on some sort of computer algebra system. You would guess a number close to that, right? You would get an approximation of a number that was close to this guy here. Using that picture, right? You'd I don't know, mouse over that bottom piece, and some graphical or some computer algebra systems would tell it what it is. You could use the table on your calculator to try to figure out values there. And then you would plug it in, plug whatever value this is into there. You would plug this into there as well, and you would see if you're less than 0.06. If you weren't, you would figure out how to make your calculator tell you an approximation with more decimal points, and then you'd plug it in and see if you got small enough. But yeah, that sort of question is not one that we're going to be exploring very much in this class. It's one that might come up a lot more if you go out and take this into applications, though. In those cases, you'll probably have better methods than just guessing and checking that we don't really have access to at this point. But that's what this question is asking you to do. Okay, I think there's one more question, and I think I can fit it here. I'm pretty sure I can do this on one screen this time. So this was from section 3.3, number 38. And I didn't write down any special descriptions, but the instructions are just to calculate the derivative, and the derivative given is d dx of ax plus b all over cx plus d. And this was in the section that has the quotient rule in it. This is definitely a quotient, so we probably want to deal with that. Now, one thing to note, this notation tells us that despite the fact that there are nothing but letters inside those parentheses, only x is a variable. The rest are constants, right? So we need to keep that in mind as we go forward. So x is the only variable. This is a quotient rule problem, so we want low is going to be the denominator. High is going to be the numerator. D low is the derivative of the denominator, which it's a linear function. And as we talked about a problem up there, the derivative of a linear function is always just the slope. D high is, again, that's a linear function, so the derivative of a linear function is always just the slope. And remember, this c and this a are constants. They might be letters, but they're still just constants. So the quotient rule says low d high minus high d low over the square of low we go. And then we can do some algebra. We can multiply through ACX plus AD minus ACX plus BC over CX plus D squared. ACX plus AD minus ACX minus BC all over CX plus D squared. ACX minus ACX cancel each other's out. So we get AD minus BC all over CX plus D squared. And that's about as simplified as we can make it. And so that's our final answer for that guy. Alrighty, folks. So this is, or next week rather, is an exam rather than a homework. So remember that there is no problem request due next Friday. We'll get back into that in 2 weeks. But there is a discussion board where you can ask ongoing questions, and I'm going to try to put out little videos more regularly. So I'm not sure. Those will I'll definitely do a batch on Tuesday and a batch on Thursday. I'm going to do what I can to get batches out on Monday, Wednesday, or Friday if there are questions there. But there's definitely going to be some on Tuesday and Thursday, so keep a lookout for those. Actually, Tuesday, Thursday, and Friday, definitely. It's just Monday and Wednesday that are questionable. And there'll probably be another one out on the weekend as well, if there are more questions. It's not required to have questions this week. You can focus on just doing the exam, but I will be doing these sorts of problem sessions more frequently, so that you can so that I can do some example problems before the day before it's due, since you don't have late passes for the exam. So I'll see y'all at various times over the next week, and good luck.